In part 2 of this project, we are going to create a Quartus project, synthesize the top module, connect the design to the FPGA pins, use the RTL Viewer and the State Machine Viewer, and in the end program the DE1-SoC development board to see how our Verilog design works. Let's create a Quartus project and program the FPGA with the easy FPGA Finite state machine. Let's open Quartus. New project wizard. Next, change the directory. We use the same folder structure as in our previous projects. We select the synth folder for the Quartus project. We type here project. Next, we browse the RTL files. We select the AZFPGA and the 7-segment decoder. Next, I select my development board from over here. Next, and finish. We first go to Files, right-click this, and set as top-level entity. Now we run the synthesis process for the first time. Okay, the synthesis process finished successfully. Let's check out the critical warnings. The first one tells us that we don't have any assigned pins for our RTL design. And the second one tells us that we need to add the Synopsys design constraint file. Let's fix this one first. We go to Tools, Timing Analyzer, File, New SDC file. And we need to create a 50 MHz clock and connect it with the CLK port. We save it. We type here project. So we can have a file called project.sdc. Save. Close. And close this also. Now we synthesize again. We see that project.sdc is present now in the files category. Okay, the synthesis process finished once again successfully. Let's check out the critical warnings again. And right now we have only one critical warning. Let's connect now our RTL module with the FPGA pins. Remember that this may vary according to your FPGA development board. For this project, we need to connect the RTL OHEX ports with the 7-segment displays connected on the FPGA development board. This is how the connections look for my DE1-SoC development board. We need to go to Assignments and Pin Planner. Let's connect now all the pins. After you finish assigning the pins, the pin planner should look something like this. Now we close it and we synthesize again. At the end of this synthesis, we shouldn't see any critical warnings. After we click the critical warnings, we can see that all of them are now fixed. Let's check out now the results from the RTL Viewer. Okay, so this is how your Verilog code transforms into a digital circuit. This is how the Quartus tool identifies a properly coded state machine. If you double click it, you are going to open the State Machine Viewer. Now you can see the initial state machine that I've used inside the Easy FPGA tutorial. This is how the state transitions diagram looks like after the synthesis process finished. We can see that we start with the off state, go into the easy state, next into the FPGA state, next into the easy shift state, and in the end in the FPGA shift state. These arrows from over here, you can see that represent the reset n assertion condition. If reset n is asserted during any of these states, then the state machine is going to enter again into the off state. This tool is often ignored even by experienced RTL designers, so if you're a beginner, you can always check if your Verilog code translated into the correct state transitions. The State Machine Viewer can be also accessed from this panel over here. Let's go again to the RTL Viewer and see how the Verilog code translated into an actual circuit in the FPGA. Here we can see how the counter seconds translated into an actual counter that has some flip-flops and some adder, and also some control logic coming from the state machine. Here we have the shift state counter represented in a similar manner. The counter seconds combined with the shift state counter are processed inside the state machine, as we have over here. Here we can see the output of the state machine that creates the decoding logic for the outputs. This is going to further control the 7-segment custom decoders. Here we can see the pipeline registers implemented over here, and in the end we have the 4 custom 7-segment decoders. that compose a purely combinational circuit. What's interesting over here, and also it was intended in the design, is to see how the pipelining stage is separating the large combinational circuit coming from the output of the state machine from the combinational circuit that controls the 7-segment display. Without this combinational circuit would be much bigger, so this will affect the synthesis results, thus decreasing the maximum frequency. By inserting these over here and splitting this large combinational circuit, we are going to be able to obtain a larger maximum frequency. Let's check out now the maximum frequency that this circuit can be synthesized at. From the compilation report, you should open the timing analyzer and click on the slow corner. You can see here the Fmax summary. Currently, the maximum frequency that this circuit can be synthesized at is 158 MHz. This is quite low. Let's see if we can improve this. When I designed the Verilog RTL code, I designed the state register intentionally to have an asynchronous reset N. Let's see what happens now if we change this to a synchronous reset N. The functionality should be the same, but we are going to use now a different flip-flop. We uncomment this and comment this one again. Save and run the synthesis again. What do you think? What is going to change? Let's open the timing analyzer again. We go to the slow corner and we can see now that the maximum frequency increased to 183 MHz. So we increase from 153 to 183. So we have a 19% increase in the maximum frequency, obtained only by changing the reset N from asynchronous to synchronous. Remember, if your design is not a safety critical app that requires a asynchronous reset N, for FPGAs you should always use synchronous reset. This gives you better synthesis results. Also, this should also help your logic to meet a better timing when the combinational circuit has a very large propagation. Let's program the FPGA now. Program device, change file, project SOF, click here, and start. Okay, we successfully programmed the FPGA. Let's check out now how our AZ-FPGA state machine looks on the DE1-SoC development board. This is how the AZ-FPGA state machine should work on your development board. Initially the design is on reset. After we make reset N equal 1, then the state machine should start working. As you can see, on the LEDs we have the current value of the state. On the 7-segment displays, we can see how the AZ-FPGA text is being displayed during the state machine changes. Pretty cool, right? If you like this tutorial, please press the like button and subscribe. As a challenge for you, please change the AZ-FPGA text to Cola Cafe, resynthesize and put it on your board. You can use the AZ-FPGA state machine as a template for more complex projects for your development board. Have fun! If you like this tutorial and you're interested in an easy path for learning Verilog for FPGA or ASIC design and verification, I gladly recommend you my course Verilog HDL Fundamentals for Digital Design and Verification. You can find the link in the video description. For more tutorials and support, you can join our Facebook community. Your strong Verilog foundation is only one click away.